All right, so 5.4 is still going over like sort of definitions of oscillators, but 5.4 deals with a dampened oscillator. So it sort of takes you through how to get the equation of motion for it, and then the position equation, and then it explains 4 different case scenarios for what is called the decay constant during it. So I'm just gonna do all that. Okay. So the first thing that we're just gonna kind of qualify is that the textbook gives us this definition that the resistive force equals some constant, so a negative of a constant times um, the acting pesty, but times the time derivative of x. So when we use that, what's basically happening with this is that a force is pulling back to equilibrium, so it'll reach equilibrium hopefully faster. Actually, it should be faster unless it's just genuinely not a dampening force. So what we'll get then is for a general form of its equation of motion, we'll end up with m times the double time derivative of x, so just m times acceleration, and then that'll be equal to that dampening force minus what we had in the earlier chapter, so that or plus what we had in that earlier chapter, so that negative kx. And then what we're going to do is we're going to move all this over to the same side of the equation. And so we're going to do mx dot dot plus bx dot plus kx. And then we're just going to define some constants here. So we're going to let d over m be equal to 2 times a beta. And we're going to use our definition of this. Whoa. We're going to let the definition of this angular velocity equal square root of k over m. And that's going to be our initial one. So it's slightly different notation, but it's the same thing that we had before. And then we're just going to divide everything by, this is equal to 0. We're going to divide everything by m, just so we get a bit more clean cut. And that x is now going to equal this 2 beta plus this omega naught squared times, this is an x dot here, and equals 0. And this is what the book has as like a significant equation. So that's the one that you're going to actually want to use whenever there's a dampening force on a oscillator. So then a quick thing that the book sort of divulges into, it takes like maybe a paragraph or two, but it then does it with circuits. So we're going to do that really quick. And what that means is that right here, this is an inductor. This is just your casual wire. And then we're going to have a capacitor and then a resistor. So this circuit is going to have the current of just that Q dot T. So Q is going to be the charge. And then over this capacitor, which is holding this q of t, we're going to see that the current will then be equal to q over c. And then over the resistor, we're going to see that the resistance times the current is going to be equal to the resistance times q of q dot of t, which is just using this right over here. And then over the inductor, we're going to see that inductive constant is going to be equal to the time derivative of the current times still that L times Q dot. So what we're going to do from there is we're just sort of going to plug it all into one equation, and I'm just going to do it real quick so that this is how it works. Plus RQ dot plus 1 over C equals 0. Okay, so it's just like a really quick thing that the book does, but it doesn't go much more into that. It's a relationship that it brings up in more sections to follow. So now that we have that, what we're going to do is we're going to go back up to this highlighted equation right here. And I'm going to write it back down here for us to use. So what we want to pay close attention to on this one now is that it is a second order derivative, which means it's going to have two general solutions that we can superimpose. So it's going to be part of that x of t equals c1 x1 of t plus c2 x2 of t, kind of a family. And we're just going to do it really quickly. So what we're going to do is we're just going to name x of t is equal to e to the rt, and then x dot of t is going to be equal to r e to the rt, and so forth. We're just going to take its second derivative now. And what we're going to do with this is we're going to plug it in to this equation here. That way, what we end up, okay, so we're going to do that, and we're going to divide by this e of rt as we do it. So what we end up getting in that form is that r squared is going to be r squared plus 2 beta r plus omega squared, omega not squared, equals z, or 0. Whoa. And what this is called is, it's called something weird. Let me type it out for y'all. It's called an auxiliary equation. So what that basically means is that its solution kind of looks like this. I forgot the word for it. I have a word. One day I'll think of it. So it's gonna look just like this. Stop doing that. So that's basically what it means, and it's gonna have those two solutions for R. So what we're gonna do is we're just gonna solve for those two solutions. So we have a R1 that equals negative B plus, the word I was looking for was quadratic formula. There we go. I knew it would pop up someday. So our first is going to be this right here. And then our second R is going to be this. And then what we're going to do with these new R solutions is we're just going to plug them in and they'll correspond with the first x and the second x. Let's finish that off. Okay. So now plugging it in, what we end up getting is that this x of t is going to be equal to c1 times, or yeah, I'm just going to plug it in and I'll give you guys the simplest form first, just because it's honestly, it is easy to see how it got there, is that they pull out that negative beta part of it just beforehand. That way you don't have to deal with it in the exact same exponent, and it also has a better property that way. So what's left inside is going to be just this. And when my computer decides it'll like to write, it'll be very easy. So what that then says is the beta is the cool part of it. This beta, we're now going to be considering to be what's called a dampening constant. So this, well, we're going to call it a decay, actually. So it's called a decay parameter. And basically, it's going to be proportional to how fast this equation is going to kind of go back to its equilibrium. And it deals with more with, since you have that E there, it's more of a limit. So the book, I would like to point out, there's like this whole paragraph denoted to it where it's like, it's gross, but it's true. So it makes, there's now 3 cases, and the first case is where B is going to be equal to 0, and that's going to be just undampened oscillation. So that's what we had last chapter, or last section, where x is just going to be equal to c1 e to the I omega t. So it's going to be a net omega naught, keeping that in there. And then plus, actually, this is not supposed to be there. I can just use some eraser. There we go. All right, so that's it for like undampened motion. That's this equation. This is any form of dampened motion. And we're going to take a look at its, just quick reminder, we're taking a look at its B. So the next possible B, next possible B would be a case where we have weak dampening. This is called under dampening, and that's where B is smaller than W. And then the book makes this distinction halfway through its derivation, but I'm just going to tell you right now that we're going to consider this beta as very much smaller than omega. The reason that we want to do this is when we're looking at omega and B's relationship, we have this is the formula that we know them to be. And we can kind of just play around with it so that if we pull out a square root of -1, they kind of swap places. And they end up like this. And we're going to name that I times omega 1. That way we can just say that this equals omega 1. But if we make the B very much smaller, then this equals omega 1. And so it's a lot kinder to us that way, and that's how the book has us look at it. And from there, we just get the equation x of t is going to be equal to e to the negative b of t times just like our C1, and it's going to look just like our undampened on the inside. It's basically undampened times that exponent there that truly makes it dampened, but only in a slight way. This is probably the most interesting case because it just goes on for a bit longer. I'm also going to simplify this using that phase shift, just so you can see it in a lot of different ways. I think this is the simplified way that comes up a lot, and that's why the book would like us to know it. And all these omegas are just going to be omega 1s because we made that simplification minus the delta. Okay. So now we're going to delete that fully, hopefully. Whoa, guys, things are happening. Okay. Okay. What we're going to do from there is, first of all, this is our decay constant or decay parameter. And what that really means is that if I have this graph right here, if I were to graph this, it'd do one of these numbers. So then my oscillation would look like this. So it'd stay within its boundaries and it'd go off like that. And then down here where that's going to be your negative amplitude. So the amplitude is this high point, basically where you start. Okay, so the next case, draw the other line to do that, is where this beta is going to be bigger than omega naught. And in that case, it kind of just stays with exactly what we had it before. Well, so it's honestly just the same equation. I'm going to write it here, though, just so it's with us. And then this doesn't have beta pulled out in the textbook. So they sort of like sorted it back in, just so you can kind of see how that looks. And then they kept our old definition of how it's going to be, so no switching the two within the integral. All right. Kind of lengthy to write all the way out, but this is what that looks like. Yeah, it's pesky. Wonderful. Okay. So what it's then going to look like as I regain control over my computer, hopefully, is just like this one day. Okay. It's going to look like that. Come on. It's going to be all of this long thing. And I'm just going to graph that for you all. So in this case, the decay constant is going to be this parameter right here. So the decay parameter is equal to this equation. So that's what's really important there. The book ends up just giving us all a chart of that. And honestly, if you don't want to see how all of them are derived, that's what I would recommend. And the graph for this just looks like it tried and then it instantly got shot down. So that's what a strong damping force does, is it just like wrecks the oscillation. All right, so the last case is called critical dampening, and that's where our beta is going to be equal to omega. And in this case, what we're left with is just two solutions. And the first solution is going to be negative beta t. And the second solution is going to be t to e negative b t. So if you want to get these solutions that derive from that equation of motion, they plug in what we're considering to be beta and then derive it from there, or like mentally plug in. But I'm just going to give them to you because honestly, knowing them is more important than knowing how they come up, at least for future chapters, because we're going to learn more things. All right, so what it's going to end up looking like is that C1 equals this negative beta t plus C2 times t e negative beta t. And so then our decay parameter is just this. So that's it for critical dampening, and those are all the situations of dampening. So that's what the textbook goes over there. And then the next section goes over driving force, which is the opposite of dampening. So dampening tries to put it back in equilibrium and keep it from oscillating, and the driving force is like, no, get out, and it tries to like stretch it out.